Okay, we'll take a look at how to set up the solution for either form of these equations, of this Rashford-Rice equation. And before we do that, let's look at the characteristics of the equation. It looks like a fairly simple thing to solve. We have a single variable and a single equation, but it ends up that solving this reliably for, in a sense, any physically realistic condition is, well, it's easy 98% of the time, and 2% of the time it can be real nasty to solve. So let's just look and see what are the characteristics of this function. Well, the first thing is that you can show, maybe I can't show, but you can show if you're clever enough, is that h of f of v is a monotonic function. Okay. That should mean that a Newton-Raphson type solution should work efficiently. We can take the analytical derivative and use that in a Newton-Raphson solution. But it ends up that there are, I believe it's n minus 1 solutions if you have n components. That's not good because you might have to go looking for all of them. That might start taking time. But luckily, only one of these yields a physical solution. And by physical solution, what we mean is that both the calculated xi are positive for all components and the calculated yi for all components are positive. There are no negative. See, whether they can be 0, I don't think, but certainly greater than they're positive, or I don't know if I should put the equal to or not, but they're at least they're non-negative. Okay, and maybe they have to be positive, but there's only one of those solutions that will give us a physical result, and that solution happens to be known a priori. That solution is the one that falls between what I'm going to call FV max and FV min, and those two values can be calculated immediately. The FV max is equal to 1 over 1 minus, and you just take the minimum k value, which we know. We can just sort through all the k values, find the minimum, and we can calculate this number. So the minimum k value might be 0.1 as an example. It'll be less than 1 for sure. But let's just say 0.1. So 1 over 1 minus 0.1 is 1 over 0.9, which is 1.1. 111. Okay? And then this f minimum is equal to 1 over the 1 minus the maximum k value. And the maximum k value might be 10, for example. Well, then it would be 1 over 1 minus 10, which would be 1 over minus 9. Minus 1 over 9 is minus 0.1111. Okay? Something like that.
Of a component.
Huh?
Of a particular component.
No, you pick whatever component gives the maximum K value. You just have to search all the K values, and you find the minimum, and you find the maximum, and that will immediately tell you what is FV min and FV max. And between those two numbers, there's only one solution. And only that solution will guarantee this. So even though there are n minus 1 solutions, we can immediately identify the bounds of the one we want. So that's good. Let's see here. I'll just kind of sketch for you what this function will look like. I'll plot f of v here. That's our variable. And then what you'll see is that from this equation here, either one of them, that if f of v equals, well, if f of v is chosen such that the denominator is 0, what do we get for the sum? If we just pick f of v, for example, if we take, what if we pick f of v is equal to make this 0, so it'd be minus 1 over ki minus 1. Let's say we have a k value of 2. So one of the components k value is 2. So this term would then be minus 1 over 2 minus 1 would be minus 1, right? So if I picked f of v as a guess of minus 1, then this denominator would become 0. And then the sum would become infinity. So you get an asymptote solution each time you do this. So you're going to have these asymptotes that I'm going to sketch like this. You know, it depends on your set of k values what these look like. I'm just going to kind of sketch one in, let's say for 4 components. Okay. And the functions will look, each time they'll come down from this asymptote like that. And then it'll go down like that. Something like that. So in this case, you'll get 3 solutions. There. And which of these 3 we want to use, that will be, if we calculate FV min and FV max, we'll find that, for example, like that. So we're only really interested in this solution. But these functions will always look like this. And another thing you can be sure of is that 0 to 1, which is a physically acceptable solution, will always lie between these. So 0 and 1 will always be somewhere between FV max and FV min. Okay. So what we can be sure of is that's always going to be greater than 1, and we can be sure that this thing here is always going to be, I should do it. This is always going to be less than, like that. Okay, so this is always going to be negative. This is always going to be greater than 1. So that 0, 1 is in between there. So let's say our 0 and 1 happen to be here. But you could still have a problem where the solution, I'm just going to do it in a different color. We could have a different set of compositions, for example, in this, for this set of k values. You could have a set of compositions that actually, this thing, when you solved it, look something like this. I can get the pen to work. Okay, so you see here the solution, can you see the little, yeah, is actually greater than 1. And that physically is saying it's single phase. It's just physically saying it's single phase. It's in this undersaturated state. Okay.
Excuse me.
Yep.
This question may maybe sounds a little stupid.
You have to
but,
speak up.
the range of the h, you just sketched the h function, yeah?
This is h. I'm sorry, should have been. This is h.
And the range of it, I think, between the minimum FV and maximum FV.
The value of h
Yeah.
goes from plus infinity to minus infinity.
No, the range of FV. You sketch some h for the values smaller than FV minimum.
Yeah.
How is it possible?
Oh, how do you get a solution there? Well, if you pick this solution, then the sum will be 0. But this value of f of e, this might be minus 6. When you put that into equations, one of the mole fractions or more will be negative. So you'll get, for this solution and for this solution, you get negative mole fractions, xi, yi.
Yeah, I know that. And I'm just speaking about just sketching the function.
Yeah. How?
We just give the value for FV.
Yeah, you
Sketch
just
the function, yeah?
give the value for FE and solve for h.
And do we have any value less than FV minimum?
Oh yeah, yeah. I can pick any FV I want. Solve that equation. F of v can go from,
That won't be FV minimum.
huh?
If we have any value.
Well, when we solve the problem, we don't need to do any f of v. We never want to use f of v less than minimum. But if you did it just to study the function, just to study and understand the general function, the unconstrained function, then you would see that it looks like this. But for practical purposes, we only want to look between here and here. Yeah. So yeah, when you actually do the solution, you limit yourself to that. But if we're just studying the function itself, it has multiple solutions. Okay. Yeah. And you might put in a different, so this is a different composition, zi here. That's a different composition, the same set of k values, but a different composition. And I might choose yet another different composition in purple, same set of K values, and this thing might go like this. Okay? In which case this f of v is going to be negative, saying it's single phase, it's a single phase. That composition, single phase, undersaturated. Okay. So then basically what it says is that the solved f of v is different cases. So if the solved f of v, if f of v star is less than or equal to from 0 to 1. It can be equal, if it's exactly 0, then it's got this bubble or drop, epsilon of the other phase. So this is a two-phase solution. Well, this would be two-phase solution. If f of v star is equal to 0, or f of v star is equal to 1, this would be a saturated single-phase solution. And if f of v is less than 0, or f of v is greater than 1, this would be an undersaturated single-phase. And what you could say, you couldn't call f of v less than 0 a liquid, but it would probably be liquid-like. Okay, so this would be a liquid-like solution, vapor-like. This would actually be liquid, saturated liquid. This would be saturated vapor. And this would be liquid plus vapor. Okay. Yep.
Don't you use the star just for the saturated?
Now I'm using the stars as the solved solution between FV min and FV max. So in this case, for 3 different compositions, I got a solved here or solved here. Those are for 3 different compositions. Yeah. So I'm just saying, once you solve the problem, that's FV star. And then if you want to figure out what does it mean, this is kind of this is what a given value of FV star would mean. And I was telling you that sometimes to solve this, you think it's monotonic, Newton-Raphson should always work, but it won't. Because in some extreme situations, particularly if you have one component where Zi is very, very small towards epsilon, Ki might be epsilon or huge. Okay. the function itself can look. I'll try to sketch it for you. Can look something like that, like a chair seat. Okay? And the zero line might be here. Okay? So what you see is that the solution you're looking for is here. This is h, the value of h is 0. And this is our f of v. And the problem is that when you're solving this numerically, that the solution between machine, the number you can use on the computer, it's limited how small it can be. Double precision is what, 10 to the minus 30 something? Okay? And the point is that if you change the value of f of v very, 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 very small, that you're still on one side or the other of this solution. So you don't see any change in the value of h. And if you go too far, then you go way back on the top side. So you're, for plus minus epsilon, you're here and here. Epsilon being the machine, computer epsilon. And so you never see, well, where, I can't get there. I can't get to the 0 within a reasonable number. You know, here you're getting a value of h of 2, and here you're getting a value of h of minus 1, and I can't get to 0. I can't change f of v small enough. So in those cases, you have to use some kind of a variable transformation. You have to do special things. It's unusual, but yeah. The other thing is, you know, your bound might be over here. You know, this is your bound. The other problem you can see is that Newton-Raphson, if you're right here, right? The Newton-Raphson, well, let's say that we're right here. The Newton-Raphson will put a derivative through there, and it'll extrapolate that derivative, that line there, to the point where it's 0. So the next iteration, it'll try this number, right? If you're here, then the next iteration, it'll extrapolate down here, and when you do this evaluation, you'll get this value. But now when you take the derivative, you get a derivative that's going completely flat, and where that equals 0, it's way, way the hell over to the right. Way beyond your limit of FV max. So your Newton-Raphson will shoot you off beyond where you can go. And then you'll say, oh, well, I can't go that far, so what do? I have to use interval halving. I'll say, well, I'm here, I can't go past there, so maybe I'll try something in the middle. And you take the Newton-Raphson from that, and it shoots you off the same, off to kingdom come. And you end up with an interval halving. You go there, and then you keep interval halving, and you walk very slowly out, very, very slowly towards the solution. Take you forever sometimes. So it can be, so the Newton-Raphson is efficient if the shape is right, but if it's not, then you're in trouble. Anyway, so these are maybe less than 1% of calculations are in this special situation. But you know, if you want a program to work all the time, you have to figure out what to do in those special situations. You guys don't have to, but people who write software. This calculation is being used in reservoir, production, drilling, pipe flow, transportation and pipelines. Everybody ends up doing these kind of calculations sometimes. So the software you use may end up crashing or saying can't converge, I can't find the solution, and then who knows what happens. Okay, any questions about this? The general setup for solution is that you have your components, basically pressure, temperature, and composition are given. You have to, one, estimate your K values, function of pressure and temperature, and then maybe convergence pressure. Okay, so that to do that, we have to estimate, or more properly, guesstimate, not a word, but assume something, or actually there are ways to come up with a reasonable estimate, but you have to figure out something there. But you need the K you need the K values. So this modified Wilson equation, or Wilson equation, in chapter, I don't remember if it's chapter 3 or maybe chapter 4. I don't remember. And then we set up a table. Uh-huh.
Can you give some sense to guesstimate the detail?
Yeah, let me finish this first and then I'll come back. So you set up the table with column in Excel I. You've got ZI. And then you have now your KI. If you want to do it the 1949 way, you set up a set of CI, which you defined. And then you have the term in the summation, whichever term you want to use, Ratchford Rice or the original Muscat McDowell, the particular term TI inside the summation, and then you sum. And that's your H value. That's the sum. But in order to calculate the term here, we have to have some guess of your F of V value. That'll be a cell. Okay? And you just put that value of F, try 0.5. Okay. You also want to calculate in two cells FV minimum and FV maximum. Right? That's easy to do. You just go through the set of K values and find the minimum and the maximum, wherever it might be. You find the K max, you find the K min will usually be down here at the bottom, and you use those to calculate the range of FV. And whatever guess of FV you have needs to be between those two numbers. And then, all these calculations, you change FV from 0.5 to 0.6, you get a different H, right? And you just keep changing. You're like a little mouse, keep changing F of V until H gets close to 0, and then you're done. Well, not quite done, because once you solve this, then you want to calculate YI and XI. So every time you just keep changing this f of v thing, that's the only thing that's going to change time and time and time again. You'll see the terms change, you'll see the h change, you'll see the yi and x change, and you know you're home when the h goes to some small number. Okay? Yeah.
Guessing two numbers wouldn't be problematic in solving this problem. I mean, if we have a wrong guess from PK and maybe the wrong answer of FP,
Yeah.
we should just change both.
This definitely will depend on the k values. Okay? But I'm not going to go there yet. This is mechanically solving the problem if you have a set of k values. Now, why you would change the set of k values, we can talk about that next week. Okay? It's just the mechanics of solving the problem. Okay? So this is so what changes as we change the value of what changes as we change the value of when red changes, all these green things change. Okay? And what we want to do is drive this to 0 or some epsilon. Okay? Now I'm running a little bit out of time to actually set up the problem, so we'll do that the first hour Tuesday. I'll set up a little problem for you. But to round off this hour, what I'm going to do is talk about two variations on the flash calculation, which are special cases of the flash calculation. Okay. And that is along the bubble point line and along the dew point line. Okay. So the special case I want to talk about is basically what's called a saturation pressure calculation instead of a flash calculation. And if it's a bubble point, I'll do that in green. Well, I'll just say that if we solve for this condition exactly equal to 0, that is a bubble point, the green bubble point line. And if we solve for the case where this is equal to 1, then that's going to be any of those dew points. And then the calculation changes a little bit because we're not searching for f of v, we're specifying f of v, we're searching for the pressure where a particular f of v is achieved. So if we do this calculation, for example, at this temperature here, we could search for this pressure where F of V is equal to 0, or we could search for that pressure where F of V is equal to 1. I could pick another temperature out here. I could search for this condition, which is F of V equal to what? 1. It's a dew point. I could try to search for this point. So in this case, we find that there are two pressures that give the same condition of F of V equal to 1. We have a double solution. Whereas on the lower temperature, we've got an upper saturation pressure that's a bubble point, and it has this condition, and this is the lower saturation pressure is, of course, always a dew point, and has this one. So let's just look and see if we want to solve for the bubble point to begin with. F of V of 0. Then what we can solve for is using the same set of equations. We'll find that what you want is that you want the sum of yi to equal 1. That's your equation. So if you want to call it h function that you want to solve for 0, h, bubble point, would be 1 minus sum of yi, and that should be equal to 0. But yi is, what is yi? Well, yi is ki times xi, right? But what is xi? That's your total composition. It's an oil. And we're just looking for the bubble. So this is actually equal to zi, ki. So yi is equal to zi times ki. And what is k a function of? Pressure. Temperature's fixed, and zi is fixed, so the convergence pressure is fixed, if you will. So these are fixed, and you're searching for P to satisfy this equation here. Because yi is a function of ki, which is a function of that bubble point pressure we're looking for. So h is a function of this bubble point pressure. This gas composition that we started with, that is our bubble. We're trying to find this bubble. There's only epsilon of it. There's a very little of it, but its composition is yi. But the yi can be expressed as xi times ki, but we know the xi is the total composition that we know. It's an oil. And ki is a function of pressure. So we end up with this equation here. One unknown, one equation. And you'll only find one solution, because the phase diagram should always look like this. And what's at the bottom, the lower saturation pressure, will always be a dew point. Okay?
To solve this problem, do we need to have some iterations?
That's right. I don't know what the pressure is. If I start here, I'll get something that is, not equal to 0. And then I'll go here. And then I'll go here. But you can actually use Newton-Raphson here also. You can solve this, or you can just use trial and error. You might go up here. Okay. But eventually you'll have to get something that drives this to 0. And then for the dew point, we've got that we're looking for this composition of the dew. It is in an amount epsilon. Okay. F of V is 1. It's actually 1 minus epsilon, but it's 1. This is the epsilon phase. It's just a drop of liquid. And we're looking for this composition, and what we know is that composition, the mole fractions, should equal to 1. We don't know what they are, but they should equal to 1. And we can rewrite xi as equal to x ki over yi. Is that right? No. That's upside down. Yi divided by ki. Like that. But we know this is equal to the total composition, because we have a gas and it's just precipitating out a very small amount of liquid. Okay, so we know the yi, that's equal to zi. We're going to divide by ki to get xi. And ki is a function of what? Well, it's a function of pressure for a fixed temperature and convergence pressure. We don't know what that is. So our h function for the dew point is 1 minus the sum of xi, should be equal to 0. And that's equal to 1 minus the sum of zi divided by ki, where ki is the function of pressure. For a fixed temperature and convergence pressure. So that's our equation to solve. If we solve it up here at this excuse me, at this temperature here, we'll find only one solution. Way down here at some small pressure. But if we go over to this temperature, we'll find one solution at 100 psi and another solution at 5,000 psi. Find two solutions. So we'll drive that H dew point to 0. You can do that at two different pressures. So it'll be two solutions. The upper dew point and the lower dew point. If you're intrigued by this, if you're interested in this, if you want to get ahead because you want to go somewhere and party next week or do something, if you have no life and just are looking for stuff to do on the weekend, Appendix B has some worked examples of this. And you can prepare for Tuesday's lecture by taking those examples, putting them into Excel, and trying to work them up yourself, instead of passively watching me do it on Tuesday. So you'll be a little bit ahead. Okay? Otherwise, you can wait till Tuesday. Okay.
Excuse me.
Yep.
In the equation that you got for bubble point,
Yeah.
shouldn't it be minus sigma ziki?
Yeah, it should be. This should be. We can replace this by zi. Oh no. Let's see. Now this was bubble point. Yeah, this we just replace.
So yi you just use ziki.
Yeah, this should be zi. Yeah. Ziki. That's right. Yeah, that's right. Anything else? Anybody else catch?